Hello and welcome to Precalculus1 review of intermediate algebra topic on complex numbers. So when we talk about numbers, we have counting numbers, we have whole numbers, we have rational, irrational, and all of those numbers integers, I forgot to mention, all of those numbers together make what we call real numbers, and we note that with that R, capital R, and you would use also negative infinity to positive infinity in the notation, right? So if you start with, it's red. Counting numbers, well, they're called natural numbers. And then there is the bigger set called whole numbers, bigger set called integers, bigger set called rational. On the side over here we have what we call irrational. So this is division of numbers. So what do we have as numbers? Counting numbers are just 1, 2, 3, 4, right? Like counting trees. You do not start counting trees by saying 0, 1, 2, 3, right? You start counting 1. If I want to count students, 1, 2, 3, 4. I'm not going to go 0, 1, 2, 3, 4. So natural counting numbers start with 1. Now, whole numbers is where we add 0 in the set. So as you can see, whole numbers contain all of the natural counting numbers, and in addition to that, contain 0 as well. Integers are going to add negative numbers into the whole mix. So we can start with -3, -2, -1, 0, 1, 2, 3, forever, right? So integers would add negatives to the game. And then rational number is any number that you can write as a fraction. And that's going to be a over b, where b cannot be 0. You see, number 7 is all of these. 7 is a counting number because eventually you get to student number 7. It's also a whole number, 7. It's integer, 7. And then you can write it as 7 over 1, which is in a fraction form. So let's say number 7 is all of these. Number -3 is only integer and a fraction, because -3 can be written as -3 over 1. So number 3 is integer and rational, because you can write as -3 over 1. But number 7 is all of the classifications we have. So that's the rational side. Then you have irrational. And irrational are the numbers that you cannot write as fraction. They have infinite decimal that never repeats, and it never ends. So numbers like square root of 2, square root of 3, pi, eventually we'll talk about e in this class. So all of these numbers are called irrational, and there is no fractional representation for them. They're not finite. So that's life, right? So now you have what you covered for what we call real numbers. So when you put these two together in one box, that is called real numbers. That's terrible. So now we have one treasure chest for all of our numbers. And then we are going to add on the side what we call imaginary numbers. So now I am going to add another box over here, and I'm going to say imaginary. Imaginary, let's give an example of 3i, or just I, or 1/2 I. You can have a negative. Let's start with negative 3i. And this I is defined as a square root of -1. This is all from intermediate algebra. Now, when you mix real numbers with imaginary numbers, you get what we have in the title. It's called a complex number. So when you put these two together, you get complex number. Complex number is of the form a plus bi, where a and b are real and I is imaginary. Now, usually we use z to denote complex numbers. So I will say z equals a plus bi. And we're going to box this. That's the form of our complex number. And now I'm going to write it again, because we have some words to learn here. This part over here is called real part, and this part is called what? Imaginary. Perfect. Part. There's just so much, or actually so many, unfortunate names. Complex numbers are not complex at all. That's first, because today we have hyperdimensional numbers. They're a little bit complex, okay?
Hyper what?
Hyperdimensional numbers.
And what?
Yeah, good luck with that. And I is actually not imaginary at all, because Nikola Tesla used that mathematics to come up with alternating currents. So there is nothing imaginary about electrical current. If you stick your finger in the outlet, you'll know what I mean, right? There's nothing imaginary about that. You're going to get zapped, right? It's a really real thing, all right? But despite the unfortunate names, right, it is very useful, and it's going to pop up a lot in our chapter 2. Only in chapter 2. Okay, only in chapter 2. You will see in chapter 2 that solutions to parabola could be imaginary. And you will get that every time when parabola doesn't cross x-axis. So you will have imaginary numbers as solutions. And we can have them also for cubic equation and so on. I will explain exactly where you get to use and enjoy complex numbers in chapter 2. They will be part of many of our examples, because they have to be. The next time you're going to see complex numbers will be in differential equations, if you go all the way there, all right? So there will be a good 5 courses, 6 courses in between that you are not going to see complex numbers at all. And then they're going to reappear. So example of a complex number would be z equals, let's say, 3 minus 2i. And the good thing to know is that the complex numbers are two-dimensional numbers because you have to graph them on a two-dimensional plane where your horizontal axis is called the real axis, and that's your good old x. And then you have imaginary axis, IM, for the imaginary part. That's not your y, okay? It's just imaginary axis. So we go 1, 2, 3 on the real axis, and then we're going to go 2 units down because it's negative 2, and this point here is 3, negative 2i. So I hope you understand why this is called a two-dimensional number. There is a dimension called real and a dimension called imaginary. It creates the two-dimensional coordinate plane, and we can draw any of these complex numbers. We can locate the complex number in the plane, right? So guys, it's not x and a y, even though real axis is x. Fine. But the imaginary axis is not y. That's important. Let's go with the blue example. Z equals to negative 2 plus 4i. Well, negative 2, 1, 2, 3, 4. And here's your negative 2 plus 4i. So you should be okay to locate these numbers quickly. So who can tell me what are the coordinates of the green dot? So I should write z equals negative 5 minus 3i. Excellent. Negative 5 minus 3i on the green example. Very good. So this is what we have for complex number as a graph. Now, guys, I understand that there are two parts, but this is all one number, right? It is one location in here. And it is all one unit. You do not get to break it apart. Yes, it does have imaginary and real parts, but all of this together is one number. Now, complex numbers could just be z equals 2i. Where would I graph that? Z equals 2i. Two up. Two up from where?
It would be on the y-axis.
Is it a y-axis? Ha, gotcha.
Or imaginary.
Yes, it's imaginary. It's hard to switch, I know. It's just I'm a terrible individual, so. So there's your 2i right there. Now see, I wouldn't be able to do this to you on a test because you would have it correct and I would just, you know. I know exactly what you meant. It's just that, yeah. You signed up for this. Complex numbers are numbers. And what do we get to do with numbers? We get to count them, okay? What we can do, if you have two numbers, you can add them, subtract them, multiply, divide, square. One we are not going to do here is a square root of complex numbers because they are really weird. Square roots of numbers, they have multiple answers and they stack like the parking garage. It's weird. So we're not going to take roots. But addition, subtraction, multiplication, division, and squaring, all of those are covered in intermediate algebra class. So let's go and add these. Addition. So if I have a complex number 3 minus 4i, and I want to add that to 9 plus 2i, how would I go about it? What do you think?
Combine like terms.
Combine like terms. Excellent. Combine like terms. So 3 plus 9 is 12. And then minus 4i plus 2i, negative 2i. Awesome. We are done with addition. That's all it is. So I'll write in blood, add like terms. Now that's terminology that you are used to. In complex numbers, if you want to be picky and you are a math major, you have to say add real parts, add imaginary parts, right? That will be the terminology. But as long as we understand each other, we're good to go. Subtraction. What do you think happens here?
Pretty much the same thing.
Same thing. Subtract like terms, which means what? Terms? No? Terms. There we go. Subtract like terms. And we are going to have, let's say, how about example 2i minus 10 plus 4i. What should I have as the answer?
Negative 2i. Or 10 plus negative 2i. Or 10 minus.
Would it be negative 10
Negative 10?
plus, or I'm sorry, minus 2i?
2i, perfect. When we distribute the minus sign, we'll go to 10 and to 4. So we'll have 2i minus 4i. That's negative 2i. And we also have negative 10. So there we go. Great. Multiplication. Say you have 3 plus 2i times 4 minus 6i. Which one? Foil, yes. Very good. Now I have to write here, and you cannot leave it. You have to use it. I squared is equal to negative 1. Right? Because if we have that I is a square root of negative 1, when you square both sides, the square will kill the root, and you have I squared equals negative 1, right? So that's that part. So now we're going to FOIL. 3 times 4 is 12 minus 18i plus 8i minus 12i squared. Now we said that I squared is negative 1, exactly. So we are going to say 12 minus 10i plus 12 for a total of 24 minus 10i. Are we all green on this? I squared is negative 1, negative 12 plus, negative 12 times negative 1 is positive 12. 12 plus 12 is 24. Add like terms. Cool? Of course, it's math. I know. The next one is division of complex numbers. And this is where fun begins. How would you divide, let's say, 4 minus 2i by 3 plus, let's say, I? Well, what is I? I is the square root, right? And how do you deal with division with square roots in algebra?
usually multiply it by itself, and then that cancels it out.
Not by itself, but you're very close. You multiply it by, it's not a reciprocal, it's called conjugate when you change the sign in the middle. So you multiply this by 3 minus I, very good, 3 minus I. So now you have two multiplication problems on your hands. You have to FOIL in the numerator, and then separately FOIL in denominator, and the complex number in denominator will be gone, right? So that's what we do. So we go and we say 3 times 4 is 12, minus 4i, minus 6i, plus 2i squared when we FOIL in the numerator, right? And then we have, now, I don't know if you see it, but denominator is difference of squares. So the middle terms will cancel. So it's just 9 minus I squared. But if you don't know that, you can FOIL, and then you will get 3i minus 3i that will cancel. So on the top, right, we have 12 minus 10i, and then plus 2 times negative 1, right, because I squared. And we have 9 plus 1 on the denominator. This is 10 minus 10i divided by 10. And now what we get is 1 minus I. Oh, this is very rare to work out. Should have bought water today. I wasted it on this problem.
Sometimes.
No, it's gone.
No, I mean, there's sometimes I
But I wasted it, I said, on this
Oh,
problem.
oh,
So
with the
if
low.
I buy it, it's just, yeah.
Oh.
Yeah.
Good luck comes in threes. You have 2 more chances. Yeah,
In threes.
I've heard that. Everything comes in threes. Good things and bad things. So you do 2 more, yeah. Good things.
So next time I buy something, I should go back to place and get my other 2 sandwiches. No. Good things come in threes, which means we are not leaving to 12, because 2 hours times 3 is 6, right? So, yeah. So we're leaving around 12 tonight. Oh, if you cause pain somewhere else, it will help. You forget the pain. Yeah, there's a pressure point right here. It's not help. So if you massage that part, it will hurt so much here. It will get out. Did you find it?
No.
No, I'll show you. Yes.
What do you say those things fall in the middle?
Oh, I'm going to define it now.
I found it.
That's, exactly. See? I am treasure like that. So the way we do division is we take the denominator and we come up with something that is called the conjugate. Conjugate of a plus bi is a minus bi. Now, if you start with a minus bi, then it will be a plus bi. So your job is to change the sign. Whatever the sign is, change it. So we have to do another division problem because it is cool like that. Let's see. How about if we divide, let's just divide 4i by negative 2 minus 3i. What is the conjugate?
Isn't it 2 plus 3i?
I'm sorry?
2 plus 3i?
Nope. Negative 2 plus 3i. We do not change the real part. Conjugate only changes the imaginary sign. That's it. So negative 2 stays as is. All right, go FOIL. Right? FOIL, and then we'll go from there.
No, it's just well,
Oh.
yeah.
Oh, whatever.
But yeah.
Are you here?
Yeah. Recently I've been playing Versus. We're still playing. It's like a roguelike.
I'll have to take a look at that.
It's a lot of fun.
I didn't know. I'm not helping you find it. I know. I'm sorry.
You know what? As long as I'm entertained, it's fine.
Yeah, the class events.
I get them a lot. I just don't have them all here.
Yes.
I'm alright. I'm fine.
Sure.
Falling asleep.
I think you should be able
It's
to-
there we go. There's just only gonna be 12.
Unsquared. Negative one and negative.
Look at it. My drive's only like 20 minutes. But
Can't miss it.
So I have a question. Can imaginary numbers appear in word problems?
Not in our first exam. The second exam, I could make that happen if you see the
Oh, no, I
request.
don't, no, I was just wondering if it was possible that they could happen like in a real life scenario. I don't-
Oh, you are not going to actually reach them in what you say a real life scenario because they are used in sciences to come up with these, like as I said, your real life is all about electricity, right?
With real
If
numbers.
Sandy took out your electricity for 2 weeks, you would probably, right?
Oh, it did,
Good.
yeah.
So you're
So
fixed,
I-
right?
Yeah.
So there was no
Yeah.
complex numbers for 2 weeks, all right? So you see that your life is really impacted by this. However, unless you are, electrical engineering researcher who's dealing with these things, then you are not gonna run into that.
Okay.
Okay?
So
that's
the only way that it would kind of be a period in like a word problem would basically be us like creating a formula.
Yes, I would literally have to go out of my way to make it.
I'm going to
So-
request you don't do that, but I was just curious if that
No,
could be a thing
that's
that
fair.
happens.
That's fair.
I gotta stop skipping ahead.
So we're going to start seeing them next class immediately, right, with the polynomials. All right, let's take a look at this problem together. We are going to FOIL. There's way too many F words in mathematics. You have FOIL, you have factor, you have functions, yeah, and then FOIL on top of everything. Negative 8i plus 12i squared divided by 4 minus 9i squared because I know the formula. Now, if you FOILed everything, eventually you had to come up with this because the middle terms canceled, right? So you had 6i and negative 6i cancel, right? Cool. So the numerator has negative 8i minus 12. Denominator has 4 plus 9, which is going to be 13. So I squared is negative 1. Negative 9 times negative 1 is positive 9. 9 plus 4 is now going to be 13. So we list negative 12 minus 8i divided by 13. Now, does this look like a form of a complex number? And the answer is no. Complex number has a and bi separated. You have a common denominator of 13. If you want full credit, you have to write negative 12 over 13 minus 8 over 13i. Now you have your a to be negative 12 over 13, and you have your b to be negative 8 over 13, right? So you are separating this. This is in the form of a plus bi. And that's the answer, right? The complex number is the answer when you split real from imaginary with whatever sign happens to be in between, right? So that's that part. Now the much easier problem, and the last problem that we cover is the problem of squaring the complex number, right? So you want to square a complex number, so you have here 3 minus I squared. How would you square a complex number?
You multiply it by itself.
Yes, very good. Multiply it by itself. So it's still multiplication FOIL problem, right? So nothing special. 9 minus 2i plus I squared for a total of 8 minus 2i. I hope. Is it? So one more time, we are going to remember that I is the square root of negative 1. I squared is negative 1. Complex number z is defined as a plus bi. We have the real part. We have the imaginary part. And then we have conjugate for division. Usually we say z bar is going to be a minus bi, which is conjugate. And that's our life. Where are we going to use this? Well, we are going to see in the next couple of lectures, it will show up number of times. The first time when we are going to see it as the roots of a polynomial for the quadratic. You remember quadratic formula, the negative b plus minus the square root? Yeah, it's gonna pop up right there a lot. Yes?
Where did the 2i come?
Yeah, that's what I was confused about. I don't know how you got that.
Oh, it's not 2i, it's 6i.
Okay.
6, yes. Please pay attention. It's clearly a 6. Thank you. Yeah, it's 6i. So, we already discussed that they are not going to come up in word problems. I already said that you are not going to see it in your Precalc2, and you're not going to see these numbers in your Calculus 1, 2, and 3. The first time you are going to revisit complex numbers will be in differential equations, Math 254, if you are going for engineering, electrical, mechanical engineering, if you're math major, right? That's where you're going to see complex numbers again, all the way, right, 6 courses from here, or 5 courses from here. Now, where we are going to see this in application for what we are concerned with, and this is just the introductory thing, is if you have some formula, right, to figure out, like, let's say, x squared minus 2x plus 20. I hope this will be enough. Let's try. So we want roots. We want, right, equal to 0, and we want to solve it. Here, solve. So the way you would do this is you would use your quadratic formula equation. Can anyone help me with this? Is equal to negative b plus minus, thank you, square root of b squared minus 4ac divided by 2a. Beautiful. So now, from this equation, we see that a is equal to nope. A is equal to, it's a coefficient of x squared, 1. B is equal to negative 2. C equals to 20. And now you plug these values. So our solutions, x1 and x2, are negative b, that's 2, plus minus square root of b squared, well, that's 4, minus 4ac, well, that's 80, right? 4 times 20 times 1. Everything divided by 2a, which is 2. So what do I have? I have 2 plus minus square root of negative 76 divided by 2. And this is where the I comes into the game, right? Now, square root of 76, the way, first what we do is we split this. So we have 2 plus minus. We split this as negative 1 times positive 76 over 2. And that is 2 plus minus I times 76 over 2. Now, is 76 divisible? Yes, it is. 76 is divisible by 4, right? It's 80, 20, 19, right? It's 19. So we can break off a 4. So 2 plus minus I, 4 times 19, divided by 2. Now 4 is going to escape the square root. We'll have 2 plus minus 2i root 19 over 2. And now you see that you can cancel the 2's. And you get a very simple compact answer. 1 plus minus I root 19. You can also do root 19i, whatever. And these are the two answers that you never explored before for this parabola. And we are going to discover what exactly this means and how it works together with what we are going to learn, right? Because most of the time so far you had the answers to be like 3 and 5, right? Or a repeated 7 or something like that. Well, now in chapter 2, we will add to those solutions complex solutions as well. So we would say that these are the complex roots. That's going to be the name in, I believe, 2.3, right? I think is when we are going to name this as complex roots. So next class, we are going to learn parabola. We are going to learn, which is x squared. We're going to learn, right, opens up, opens down. We're going to learn look again into shift up, shift down. We're going to look into the domain and range, and we're going to look at line of symmetry, and a couple of things that we need to know for parabola. That's all next class. So see you then.